Hello everyone, my name is Krish Narain Kapoor. I'm a third year student at IIT Roorkee, and today I'm going to give a presentation on noise reduction techniques as part of my course PHN 313 Signals and Systems. So let's start. This is the content I'm going to cover in this video. First, I'm going to start with introduction to noise and signal processing. Then I'm going to talk about types of noise based on frequency spectrum. Then give an overview of noise reduction techniques. Then I'm going to talk about two noise reduction techniques in a little detail. So, what is noise? Noise refers to any unwanted disturbance within a signal that obscures the information it carries. Like here, we can see our signal, which does not have any noise, and here is a signal in which noise has been introduced. As we can see, our signal is now obscured or distorted. So, what are the so we have various types of noise based on their frequency spectrum. We have white noise, band limited white noise, narrowband noise, colored noise, impulsive noise, transient noise pulses. Uh, so these are some types of noise reduction techniques. First, we have filtering methods. In these, we literally just filter out the noise from the signal. Uh, in this, we use filters like high pass filter, low pass filter, band pass filter, and band stop filter, and some other filters. Then we have adaptive filters. Adaptive filters, they adjust their parameters in real time based on the input signal characteristics. Then we have transform-based techniques. These techniques convert signal from time domain to frequency domain or wavelet domain. Uh, and then separate noise for more efficiency. Then we have nonlinear techniques. We apply nonlinear techniques like medium filtering to reduce certain noise types like salt and pepper noise. Then we have let's talk about a technique called DFT noise reduction technique. It stands for discrete Fourier transform noise reduction technique. What this technique does is uh, it reduces noise by transforming the signal from time domain to frequency domain, where the noise components can be more easily identified and removed. The basic idea of this technique is to exploit the fact that noise occupies different frequency bands than desired signal, allowing for selective filtering. Uh, let's go step by step. Let's explain the DFT technique step by step. First, we transform the noisy signal to the frequency domain. We apply the discrete Fourier transform to the noisy signal to convert it from the time domain to the frequency domain. This gives us a frequency spectrum where each point represents the magnitude and phase of a particular frequency components of the signal. The DFT of a signal Xn is this, uh, where this Xk represents the frequency component at index X and N is the number of samples. Then our second step, we identify the noise in the frequency domain. We look at the frequency domain which we have obtained and uh, mainly try to characterize a noise as high frequency noise, frequency noise, etc. Noise is generally presented as high frequency component with small magnitudes, whereas our desired signal might be concentrated in specific frequency ranges. We analyze this frequency spectrum and identify the frequency bands dominated by noise, which are often the high frequency components. We then filter the noise components. We apply an appropriate filter uh, in the frequency domain to suppress or attenuate the noise components. This filter preserves the frequency components of the desired signal while reducing the noisy components. Uh, some common types of filters are low pass filter, which removes high frequency noise, band pass filter, which keeps frequency components with the desired range and filters out everything else. Then we have thresholding. Magnitudes below a certain threshold are set to be zero. This re this filters out our low frequency noises. So the next step is once we have filtered out our noise, we apply inverse uh, discrete Fourier transform on the signal to convert the signal back into the time domain. This is a formula for the inverse discrete Fourier transform here. This step then reconstructs the time domain signal with reduced noise. Some advantages of DFT are it allows for frequency selective noise reduction, like we can have a specific range of frequency in which noise is present, and we can filter it out without affecting our entire signal. Uh, then we have it is effective for stationary noise. It works well in environments where noise characteristics remain relatively stable over time. Here are some applications. DFT is used in audio signal processing to reduce background noise, hums, and other frequency-specific noise in recorded audio. Uh, these in audio signal processing, our noise is basically just low frequency noise. So we can just apply a high pass filter or a threshold filter and uh, remove the noise from the signal. Image processing to remove periodic noise patterns from images, DFT can be used. Communication systems to remove noise from modulated signals and enhance the signal to noise ratio. Some challenges while using DFT are that it does not work for dynamic noise. Dynamic noise is basically noise which changes in real time, uh, like our input signal keeps changing and the noise with it also keeps changing, and DFT can't keep up with that. So for that we have some other techniques like adaptive filters. Uh, an adaptive filter operates by adjusting its coefficients to minimize the error between the desired output, which ideally is noise-free, and the actual output of the filter. The adjustment is based on an algorithm that updates the filter coefficients according to the signal and noise environment. Here we can see, according to the signal and noise environment, our adaptive algorithm updates the filter coefficients, which then updates the which then updates the filter, and the input signal is filtered to a reduced noise output. Some common types of adaptive filters are least mean square filter, normalized least mean square filter, recursive least square filter, and Kalman filter. Uh, now we are going to talk about the RLS filter system. Uh, Here are some of the components of the RLS filter system. Components or coefficients which are used to change which are changed to uh, suit the noise of the input signal. First, we have error signal. This is the difference between the desired signal Dn and the filter's output Yn here. Desired signal. This is a signal we wish to estimate or retrieve after noise reduction. Then we have filter output. This is the output produced by applying the adaptive filter to the input signal. Then we have input vector Xn. This includes our current and previous input samples, where this is the formula, where m is the number of filter coefficients. Then we have filter coefficients omega n. These are the weights or parameters that the algorithm updates at each iteration to reduce the error signal. Now let's talk about the working of RLS algorithm. First, we initialize it with our filter coefficients omega 0 usually set to 0 or some small random values. Then we then our initial inverse correlation matrix is typically initialized to a large positive diagonal matrix. Common initialization is P0 is equal to del raised to power minus 1 I, where I is our identity matrix. Here we have kept uh, del small in a del to be a very small positive constant, such that del raised to the power minus 1 is del raised to the power minus 3 or larger. Uh, and of course, I is an identity matrix of size m cross n, where m is the filter order. Now, then we compute the filter output. At each step n, the output of the adaptive filter is computed as yn is equal to omega t n minus 1 xn, where omega n minus 1 are the filter coefficients from the previous step, and xn is the input vector containing the most recent and past samples. Then we compute the error signal. The error signal is the difference between the desired signal and the filter's output yn. This is the formula for our error signal. Here we have just used the formula of yn here. Uh, this error signal drives the adaptation of the filter coefficients. Then we have gain vector calculation. Uh, the gain vector calculate controls how much the filter coefficient should be updated based on the error. It is computed using the inverse correlation matrix p raised to p n minus 1 and the input vector xn. This is the formula for the gain vector, where lambda is the forgetting factor, which determines how much weight is given to recent data compared to older data. Typically, lambda is between 0.95 and 1. Then we update the filter coefficients. The filter coefficients are updated recursively using the gain factor Kn and the error signal En. Here are the new filter coefficients for this recursion. This step adjusts the filter weights to reduce the error. Then we update the inverse correlation matrix. The inverse correlation matrix represents the memory of the algorithm which contains past correlations of the input signals. Is updated at each time step. Here is the formula for the new updated correlation matrix. This update ensures that the algorithm accounts for changes in the input signal. Then there are some advantages and disadvantages of RLS technique. One advantage is rapid adaptation. RLS adapts quickly to changes in signal or noise characteristics, making it suitable for real-time applications. Low steady-state error. The algorithm achieves a low residual error once it has converged. Then we have some disadvantages. One disadvantage is that because RLS requires matrix inversion and updates, which are computationally intensive for especially for large filter orders. It requires a very strong computer system in order to operate. Then we have stability issues. Poor choice of the forgetting factor lambda or initialization of P0 can cause numerical instability and not give us the desired result. That's it for the video. Uh, Thank you.